Let's play guess the fake. Go.
That one.
They're both real. They're balls.
What?
Hello world, it's Siraj. In this episode, we're going to talk about generative adversarial networks. Deep learning has done a lot for us, but its most incredible successes have involved discriminative models. Discriminative models are great for classification tasks. They discriminate. Not in that way, obviously. Models like neural nets support vector machines and hidden Markov chains where we map high-dimensional, rich sensory input to a class label. A discriminative model doesn't care about how data was generated, it just categorizes a given signal. They're the secret sauce behind tools like facial recognition and the language translation and sentiment analysis. But there's another type of model that hasn't been as successful, the generative model. Generative models are harder to get right due to the difficulty of approximating some really hard probabilistic computations. A generative algorithm does care how data was generated in order to categorize a signal. It asks the question, which category is most likely to generate this signal? Anytime you'd like to generate some novel data based on some input data, whether that be a chatbot's replies or a song or even a short story, generative models are the way to go. So what is a generative adversarial network, or GAN? Well, GANs were introduced by a straight G named Ian Goodfellow who didn't give a bite. The basic idea is this. You have two models, a generative model G that generates new data and a discriminative model D that estimates the probability that whatever sample data G shows it came from training data rather than G itself. They're essentially playing what's called a mini-max game. Mini-max is a well-known strategy of always minimizing the maximum possible loss, which can result from a choice that one of two players can make. So G is fed a bunch of training data and attempts to generate new data based on that input. Every time G generates a new sample, D will try to determine if the sample is from the model's distribution or the training data distribution. Think of G as a counterfeiter and D as the police. They're adversaries. G will keep trying to produce fake currency and use it without detection, while D tries to detect if it's counterfeit or not. This keeps on happening, and both models improve their methods until eventually the counterfeits are indistinguishable from the real thing. So what type of model do we use for D and G? Well, many different types of models can be used. In the original paper, the author used something called a multi-layer perceptron for both to generate photorealistic images based on a training dataset of images. But there's an even more interesting paper that came out that used GANs that I want to talk about. It came out just last month and it's called Generative Adversarial Text-to-Image Synthesis. These guys created a GAN that can generate a photorealistic image based on a caption. I am dead serious. So when it was given the caption, a large blue octopus kite flies above the people having fun at the beach, it was actually able to generate an image that showed just that. So how did it do this? Well, they used a dataset of images and their associated captions as the training data. First, they had to encode the data before they fed it into the models. They used an encoder which was a hybrid neural network called a character-level convolutional recurrent network. It takes both the image and the caption as input and creates a joint representation of both in multimodal space. It does this for both the generator and the discriminator. Both models are a deconvolutional feed-forward neural network. Once they had the encoding, they fed it into both models and each generated an image. The generator net creates a synthetic image from the embedding, an image that is close to the real image but not quite. The discriminator net receives three inputs: the real image with the right text, the real image with the wrong text, and a fake image with the right text. It encodes each of these and compares them to what the generator shows it, looking for a similarity between its inputs and the generator's outputs. Each time step, it will try to determine if the generated image was synthetic or real by doing this comparison. After the determination has been made, the weights of both the discriminator and the generator are updated, so they both get better over time. By the time training is over, the generator will be pretty good at fooling the discriminator by producing photorealistic images that look like they must have come straight from the training data. So let's build our own GAN. We're going to build a simple Python script that demonstrates how GANs work. Both models will be represented by learning Gaussian distribution curves that we plot using PyPlot. Once we have our dependencies in place, we'll want to define our hyperparameters. These are all different activation functions that will apply to our models at some point. We'll also want to define how much we want to train our models, as well as the number of hidden layers we want them to have. We'll then write 4 helper functions. The first 2 will help us visualize our Gaussian curves in our plot. G builds the generative network, and D builds the discriminative network. We'll initialize our networks, then write a plotting function to plot both curves. Finally, we'll train our network using a for loop. We'll draw samples from a uniform distribution, then train both networks at different intervals. We'll plot the graph as we train our model so we can visualize the result. Let's see what it looks like as it trains. As it trains, the generator curve will look more and more like the true data distribution curve as it tries to fool the discriminator network. And there you have it. You might be wondering, what are the real-world use cases for GANs? Well, GANs Gaming is one. It's a daunting task to create a huge 3D map manually, but with GANs, programmers can write a part of the map and generate the rest. Another is interior design. If a designer wants to visualize what a room will look like, they can just ask the machine for a photo of, say, a living room with beige sofas facing each other and 4 ninjas in the scene. Pretty much anytime you need help visualizing anything, GANs can help fill in the gaps and augment your own imagination. I've got some great links for you in the description. Please subscribe for more ML videos. For now, I've got to go fix a deadlock, so thanks for watching.